Good day, everybody, and you're all most welcome to this week's CNPS technical session. Now, regular participants will be aware that we've been hosting a series of lectures, actually, by Vladimir Nechil-Tylo, a number of parts actually on his world universe model, and in fact that will be going on for some weeks. The next one will be in 2 weeks' time. But we've taken a break. There's a lot of information in Vladimir's lectures, and we've deliberately actually taken a break, and we've invited Sephan Gift back. Now I say back because he gave us a talk some time ago on the Selleri transforms, which are proposed transforms between inertial frames, basically in preference to the Lorentz transforms, which would be Stephan's argument. He's kindly agreed to come back today. The last time he actually demonstrated 5 tests where the Lorentz transformations would appear to fail miserably, and the Selleri transformations seem to conform with reality. Now, he's going to give us another 5 tests. And of course, this is the Atmos test, the litmus test, the acid test. If something doesn't accord with reality, it doesn't matter how beautiful it is. It doesn't matter how many authorities have staked their careers on it. It's thrown out. You must conform to reality. So that is what Sephan will be looking at. Sephan is based in Trinidad and Tobago, and I see it's lovely weather there. I see the sun was shining through his window. But I was just saying myself, even though I'm based 53 degrees north of the equator and we've had a lot of rain and cloud, the sun is shining through my window as well. So so it's not too bad a day here in Dublin either. Now, okay, so just to tell you, we've entitled at Stephan's behest, the lecture today, A Modern Approach to Space-Time Physics. So it's argued what needs to be used today, as distinct from what was used historically. And maybe to go through this, maybe repeating a lot of what I've just said. In the first presentation, A Modern Approach to Space-Time Physics, it's actually the same title a few weeks ago he gave. We showed that the Lorentz transformations of special relativity, despite their almost universal acceptance, fail 5 straightforward tests. In this presentation, we show that the Lorentz transformations fail 5 additional tests. These tests are, and just to give you a heads up on it so you can be aware of it when Sephan comes to these points, are simultaneity, Sagnac effect, Selleri paradox, right-angle lever paradox, and the correspondence principle. We also show that the Selleri transformations involving a preferred frame and available in the mainstream physics literature pass these 5 additional tests, as they did the 5 with no paradoxes. We therefore advance the Selleri transformations as the space-time transformations that best accord with the physical world. Now, we'll have a longer discussion and we can all give our own viewpoints on it. I'll just say a word or two, just my own, perception about black and white. Now, if I get anything wrong or I've misconstrued anything, Sephan can correct it in his lecture. But I've looked at this. I mean, this whole business of being concerned with what are the equations that would transform one frame to another inertial frame where one is moving with constant velocity relative to the other. This whole question, I suppose, became important with the advent of Galilean relativity, with Galileo looking at maybe a ship progressing on water at a constant velocity, and one could perform mechanical experiments in that, but one wouldn't be able to distinguish that one wasn't moving. One could be on the shore and would get the same effect. One drop a ball and the ball would fall to the floor of the ship in a straight line, and so on. So the Galilean transformations are the more intuitive ones, which are used normally in mechanics. And this whole business of Lorentz and so on came. It was actually Henri Poincaré who called these equations Lorentz, because there were earlier people like Voigt, for example. He might have been one of the earlier people dealing with these transformations. So it appears to me, and this is where Sephan can correct me if I'm wrong, but it appears to me that the Selleri transforms are a bit of a hybrid between the two. They don't go quite as far as the Lorentz transformations in introducing a spatial coordinate dependence on the transformation of time. But they do otherwise bring in things like length contraction and time dilation. So we'll do it. Now, just before introducing Sephan again and giving the floor to him, I just must mention again that practicalities about running the whole show and the CNPS and all the servers we have and so on. The membership dues don't actually totally cover the running costs. So David de Hilster has recorded a little, it only takes a minute or two, video, which I'll just play for you quickly now, just about a fundraising endeavor, which has been actually reasonably successful, I might say. So there it is.
Hello, my name is David de Hilster. Hello, my name is David de Hilster, and I'm president of the John Chappell Natural Philosophy Society. Hello, my name is David de Hilster, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science, from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough, and that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear, and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
Right, now that's out of the way. So all we have to consider before starting is that, as usual, and I have discussed this with Sephan again, the normal format is quite acceptable. In other words, the people mainly on the social media will be putting in discussions and questions and answer. If there's anything specifically you want Sephan to address, please put this as a question so we don't miss it. But we'll deal with those first. We'll try to highlight the questions, and then we'll get Sephan to address them. And then if you want to come back, you can do that. So the lecture will occupy something like 1 hour. We have 2 hours altogether. Well, a little less now because we've had preliminaries, but it'll occupy up to an hour. And we'll have almost an hour of discussion and questions and answer. So when we've absorbed the main questions, we'll then get to more detailed discussion, and we'll be inviting people in the green room to talk. So there should be plenty of time for that. And excuse me if I sort of lean down and start looking at the comments, because people are coming into me, and maybe some things are urgent or some things to be dealt with later. So that's all that's about. Okay, now, Sephan, good to see you again.
Thank you.
Would you like to try sharing your screen so you can put your visual aids up?
So just tell me again, Ian,
so
where do
at the bottom there should be a banner saying mute, stop cam, settings.
Yes.
Present. Okay, just say present.
Present. Okay.
Now here there are a few options. I think it's probably safest to
share screen.
Share screen, yeah, because otherwise the slides have to be up somewhere. So share screen. Now you may have to click that twice, Stefan. You may get a sort of like an image of a screen, and you may have to click that. It may say, "Do you want the whole screen or what?" So you
All
have
right,
to do it twice.
let me do that again.
Yeah,
Uh-huh.
I'll
Share,
know when you've done it because I get a banner here, but I have to put it up. You won't see it immediately.
share screen.
Share
Then I
screen.
see.
Yeah. So
And
then you'll see sort of like a rectangle somewhere.
yes.
A couple of rectangles, and you have to click on one of those. It might be your entire screen.
Well, it says here. Let me see.
Let me see if I can do it as well to see what comes up.
Choose with what to share with
Yeah,
StreamYard.
so it's probably your entire screen. I think you may have to click at the top right-hand side.
Yeah.
And then when you do that, you'll probably see. You'll probably see the screen, but you'll actually have to click on that as well. My understanding is. Let me see. I think we're getting something.
I went through the process, and it.
Yeah.
It's. I believe it's supposed to be sharing there, Ian, but I'm not seeing it up.
And neither am I, Stefan,
It's-
because
it says here StreamYard.com is sharing your screen.
It may take a moment or two.
Okay.
So I'll just say, are there any new comments? And yeah, okay, nothing. Okay. Let me see. Nothing happening. Is it?
Nothing happening.
I heard. No. Okay. Well, the other way to do it, I'm surprised that didn't work, is you can share your slides.
All right. So I'll stop sharing. It says there's something here which says stop sharing. I've done that.
Okay.
Let me go back to present again.
Okay.
Share screen. I'll go to slides then.
Okay.
It says
I hope this works because normally we do it the other way.
Oh, Lord. Goodness.
So if you have your slides in a particular location, you should be able to click on that.
It's saying I asked you to share your slides, to share slides, and it says you have no slides, but the slides are up there. So
do you see your computer at the very end of that?
Yes.
Okay. Click on that and navigate to wherever you have your slides.
All right. We can currently, it says upload file. All right. Let me go to the desktop.
Right. If it's on your desktop.
Yeah. I actually have the slides open, but PowerPoint presentation. All right.
Either of these systems should work, actually. I don't know why the other one didn't. Just I ask people to bear with us because they're always have these teething problems. We will sort it out in a moment now. Now wait a minute. Something's happened.
Are you seeing it? Yeah. Okay.
Well, I put it up now. Is that it?
Yes.
Okay. So and what? So you should have control. If you don't, just shout and I'll do something. But the main thing is I'll get rid of our photographs, but I'll keep the video, your audio on, obviously. So we can maximize this to the screen size, you see. Let me see now. Forgotten how to do that. Well, what I'll do actually is I'll remove myself, which means if you need me, just shout. I'll come back. Okay, and I'll give you the floor. There.
Okay. All right. Can I proceed then, Ian? Ian, are you there? I'm not hearing you.
Sorry, you're not hearing me. I was speaking.
I'm now hearing you. Now that your image was, are you hearing me?
I'm hearing you perfectly. Yeah. No, I removed myself so you couldn't hear me. I was silent.
Oh, I see.
All I do is I'm going to disappear again. I'll be silent. I can hear you perfectly. We can hear you.
Okay, great.
The only thing I'll do, with your permission, is it'll take me a moment, but I'll probably remove your photograph so that the slides occupy the total screen.
Okay, sure.
Okay, fine. Apart from that, we can hear you.
All right. All right. Well, good morning, everyone, Ian and the entire group. And thanks again for allowing me to present my ideas on space-time physics. This is the second presentation. The first one I had done some time ago. And everyone. So a modern approach to space-time physics was the first one. And I call this a modern approach to space-time physics 2, because I have additional information. For those who were not present at the my first presentation, I am a professor of electrical engineering at the University of the West Indies. It's a university with 5 campuses, one of which is online, with over 50,000 students. I conduct research mainly in electrical engineering, but I've spent some time in space-time physics. And I'll be presenting information on that this morning. I have published one textbook with Professor Brent Mundy from the University of Calgary, Electronic Circuit Design and Application. It's now in its 2nd edition, and it's doing quite well on the open market. So today's talk, we show that the Lorentz transformations of special relativity, despite their universal acceptance, excuse me, fail 5 more tests. These are simultaneity, the Sagnac effect, Selleri paradox, right-angle lever paradox, and the correspondence principle. We again show that transformations involving a preferred frame developed by Franco Selleri and published in the mainstream physics literature are successful with these and other tests and produce no paradoxes, a very key point. We therefore advance the Selleri transformations as the space-time transformations that best accord with the physical world. Excuse me. Now, just once again to define the problem, where one author calls it the central problem of relativity, which is to find transformations connecting 2 inertial frames, one an inertial frame S and another one S we call S prime, which is moving relative to S at a velocity V as shown in the diagram. And we all know we've set this up before, so we know what we're referring to. They initially, at the start of the events, they are coincident, and then the S prime frame moves along the x-axis of the S frame. Now, I also indicate there that in the S frame, light speed is c, and I will come back to that in a minute. So this is the problem, to find transformations that connect S to S prime. Okay, that's the problem before us. Now, those transformations must reduce to, Ian mentioned the Galilean transformations, when that velocity v is very much less than the speed of light, with v not equal to 0. And I've indicated the Galilean transformations there. And we demand that because our experience over time has been that the Galilean transformations satisfy our circumstances and hold to be true at low speeds. So therefore, we are very comfortable with them. They've worked for many, many years. And therefore, any transformations that replace them must reduce to the Galilean transformations when the speeds are very low. So that is a requirement that any new transformations must satisfy. It's actually called the correspondence principle, which I have as a test later on. Now, to answer this question, Einstein used two postulates. he used the principle of relativity and the principle of light speed constancy, and he came up with the Lorentz transformations, which you see there. We know them very well. And because in the case of the Lorentz transformations, the principle of light speed constancy holds, it means that all of the inertial frames, S prime, and all inertial frames have light speed c. Therefore, there is no preferred frame. There is no single frame that you could single out compared with the others. So that's why I've indicated there with the Lorentz transformations, there's no preferred frame. Selleri used 2 experimental facts rather than 2 postulates, as did Einstein. Selleri used 2 experimental facts, two-way light speed constancy and dilated muon decay time. And with those 2 facts, he developed what I refer to as the Selleri transformations. He calls them the inertial transformations, but and while they existed before, he did a tremendous amount of work on them and provided a sound basis for them being the valid transformations. So in honor of his work and his publication of these transformations, I refer to them as the Selleri transformation. And with these transformations, there S is a preferred frame. It is the single frame where the single inertial frame where light speed is c. None of the other frames in general have light speed c, as we shall see. All right, well, in fact, I did that the last time. We're not going to deal with that this morning, but in fact, that is the case. Only one frame has light speed c, and that's why we call it a preferred frame. Now, previously, there were 5 correct predictions of the Lorentz transformations and the Selleri transformations, which I discussed the last time. There's transfers. So this is to indicate that, in fact, the Lorentz transformations do have made a contribution. They have predicted some correct phenomena. And these here I listed are the transverse Doppler, relativistic beaming, Compton scattering, relativistic elastic collisions, and Thomas precession. These are 5 phenomena which the LTs, the Lorentz transformations, correctly predict. And I'm also indicating there the Selleri transformations also correctly predict them. I remember, and Ian made this point at the start of the exercise. He said, you know, the acid test, the gold standard for scientific work is that your theory must make predictions, and then these predictions have to be tested. And if the prediction fails the test, then the theory has to be discarded. So that the transformations must make predictions, and those predictions must hold true. This is the case with these 5 phenomena, and I like to put up this diagram of Thomas precession where you see an electron going around the atomic nucleus, and the spin of the electron is precessing about the spin axis there. That actually comprises, that precession is 2 components. There's a component called Larmor precession, which occurs when the electron is immersed in a magnetic field. And then there's the Thomas precession, and together they result in the overall precession that you see. Okay. Now, there are 5 failed tests of the Lorentz transformations, which I went through in my last presentation. One was the one-way speed of light, where I used the synchronized clocks of the GPS to test and demonstrate that light travels faster west than east. That's a very clear statement. There's no ambiguity about it. It's either true or it's not true. And I'm contending that the synchronized clocks do demonstrate that light travels faster west than east. So that's one of the failures. And of course, the Lorentz transformations predict constant light speed. So they fail that test. Then there's the time transformation. The time transformation of the Lorentz transformations is negated by again, the satellite clocks of the GPS, which adhere to or are governed by a time transformation that is different from the Lorentz time transformation. And I went through that the last time and showed, in fact, experimentally, the time transformation or the time equation that those satellite clocks obey is not the Selleri time transformation. And therefore, again, the Selleri transformations fail that test. Then there's GPS clock synchronization. Again, there's an equation which is used, and it's in Ashby's paper, which I referred to the last time, that is used to synchronize clocks. So ground-based clocks have to be synchronized, and to synchronize them, that equation indicates the time between light moving from one place on the surface of the Earth to another. That equation cannot be derived using the Lorentz transformations, which predict constant light speed. If you use constant light speed, you will not get correct synchronization, and a correction has to be added. The Selleri transformations predict non-invariant light speed, and when you use that equation, you can get the synchronization equation. And in fact, there's no correction required when you use the Selleri transformation to derive that clock synchronization. So again, the Lorentz transformations fail this clock synchronization test. The GPS engineers talk about this correction that you need and make it seem as though, well, that's a valid representation of what is taking place. No, if you use the correct light speed, you do not have any you have accurate clock synchronization. If you use constant light speed, then is when you have inaccurate synchronization and have to add a correction. Then there's the Michelson-Gale experiment. I indicated in my talk, the textbooks are silent on this experiment. This experiment was performed in 1925. That's what, close to just 99 years ago, and yet none of the textbooks, well, I couldn't find any. So let me say, it's rarely ever seen in the textbooks. I have never found it, but I really perhaps shouldn't say that it's not there because I haven't looked at all the books. But it's certainly hard to find. And the reason for that is that the Lorentz transformations predict constant light speed. So in all the arms of the Michelson-Gale experiment of the apparatus, constant light speed is what is predicted. And therefore, light beams going around, counter-propagating light beams in the Michelson-Gale apparatus are going to have the equal time to traverse the apparatus, and there will be no difference in time propagation, and hence there will be no fringe shifts. And that is the problem the special relativists face in explaining the Michelson-Gale experiment, as a result of which they do not deal with it at all. They're silent on it, but clearly the Lorentz transformations fail that test. And then the last one is the Wang experiment, which is counter-propagating beams in an moving optical medium, and it fails there again for the same reason. It predicts constant light speed, and once you have constant light speed in both directions, you are not going to have any time differences in the light propagation. So these are 5 failed tests of the Lorentz transformations, and I should tell you the Selleri transformations pass all of them. Today, I'm going to talk about 5 more failed tests, and we listed them as simultaneity, the Sagnac effect, Selleri paradox, right-angle lever paradox, and the correspondence principle. So let me move along quickly. So the first one we're dealing with is simultaneity. The Lorentz transformations predict relative simultaneity, and the equations I have there really are equations to indicate how we arrive at that. So this is the time transformation, the Lorentz time transformation for 2 clocks. T1 prime is this clock C1 prime, which is coincident with C1. This is the moving frame and this is the fixed frame, and I have separated them only so that you could see the separate clocks. This one, the time on this clock is given by this equation, and the time on the second clock corresponding to T2 prime, corresponding to the C2 prime being coincident with C2, is T2 prime. And when you subtract them, you get this last equation here, which indicates that there's just a minute. There's something coming up on my screen. Oops. All right. I need to just go back. Right. Yeah. Good. The difference in the time in the moving frame is given by delta t prime is equal to that, what you t2 prime minus t1 prime. And even though I set t1 equal to t2 in the fixed frame, in the moving frame, the time difference is not equal to 0, as you can see from that equation. Okay? Because x1 is not equal to x2. They are displaced, they are separated. And that is what is referred to as relative simultaneity, which is that, one second, predictions of the LT's spatially separated events that are simultaneous in S are not simultaneous in S prime. And I have even brought to the attention of some of my colleagues on the email that in Sartori's book, Understanding Relativity, he has an example there where the order of the events in S are actually reversed in S prime. So that something that happened, an event that occurs in S, and there's a later one in S prime, in S, sorry. When you go to S prime, the order of occurrence of those events is reversed. So future events occur before past events in S prime, which is an absurdity. Anyway, so that's the prediction of the LTs. That's relative simultaneity. Good. With the STs now, the Selleri transformations, when we go through the same exercise, we find that the time difference for clocks in the moving frame is the same, is 0 once the time difference is the same, is equal to 0 in the fixed frame. So using the Selleri time transformations, when you make the subtraction, you get that the time difference in the moving frame is 0 as it is in the fixed frame. And what that means is that spatially separated events that are simultaneous in S are also simultaneous in S prime. There's no reversal of the order of events from S to S prime, I should also mention. So the LTs predict relative simultaneity, the STs predict absolute simultaneity. Fortunately, we can use the GPS to test, which is true. This is hard. I've never seen this mentioned anywhere, but this in my examination and investigation of the GPS, this is true. And I will just read out what I have there. The GPS network of synchronized clocks enables global or absolute simultaneity on or close to the Earth. Relative simultaneity resulting in two clocks at two different locations in a satellite having T1 prime not equal to T2 prime. That the T1, the prime means the time on the moving clocks on the satellites. We never find that to be the case once T1 is equal to 2 on clocks that are stationary in the ECI frame, despite movement of the satellite. According to relative simultaneity, those moving clocks should at some point become, go out of synchronization. They should indicate different times because of the effect of relative simultaneity. That is never observed. In fact, I say lower down, if it existed, specific clock adjustment would have to be introduced in the satellite clocks in order to maintain synchronization among all the clocks in the network, so as to prevent the system from being rendered inoperable. No such adjustment is ever used in the GPS, thereby confirming relative simultaneity does not exist. Simultaneity is absolute. I'm moving along now to the Sagnac effect. And what we have here is a rotating disc, the solid circle. And it's rotating in the clockwise direction. And we have two light beams, one in going in the counterclockwise, which is this beam here. And then the other one going in the clockwise direction, which is this one here. So you have two beams. And what has been found experimentally is that the time difference between those two counter-propagating beams is 2LV over c squared, where L is the circumference of the path, and V is the velocity or speed of the periphery of the rotating platform. And that is what has been experimentally confirmed. What you see on the slide there is what has been confirmed experimentally, as we all know. Now, let us see what the different transformations say. The Lorentz transformations, I go through a process there to derive the speed of light on using the Lorentz transformations to find the speed of light at a point on the disk, on the periphery of the disk. And it turns out to be, with a simple derivation, that light speed is c. And we ought not to be surprised by that, because that is, the foundation of special relativity, that light speed is constant. Well, once again, if the light speed is c, then it means the beams propagating around the disk take the same time to propagate. So the last equation there shows that the difference in time, I'm just having a little problem with some